So I mentioned in the first video in this chapter that intermolecular forces allow you to predict and explain a lot of different physical properties of substances. And the general trend for London dispersion forces is that they're going to become stronger with increasing molar mass and elongation of the molecules. This essentially allows more interactions, more surface area between molecules, resulting in stronger forces. Okay. So if you're talking about nonpolar substances, those are only going to have London dispersion forces, right? They're not going to have hydrogen bonding because that would be polar. And they're not going to have dipole-dipole interactions because those would also be polar molecules. So when we're talking about nonpolar substances, molar mass and molecular shape are the key factors that determine their physical properties. So if you think about the boiling points of these, let me just list them here. The lowest one at 69 degrees centigrade is hexane. That's a C6 carbon chain, all carbon hydrogen in all these molecules, okay? So that means they're nonpolar, but they have different shapes, right? Hexane has the lowest boiling point. Compared to octane, it has a much higher boiling point. Octane has 8 carbons here. And so it has lower molecular weight, hexane does. And so there's less interaction. The hexanes interacting with each other, it's a small little area. But then you get to octane and it's much longer. So there's more instantaneous dipole, more forces, more London dispersion forces. That's going to cause the molecules to stick to one another more, right? And so it's going to be harder to boil, harder to go from liquid to gas. Compare that with isooctane. That has more this like branch structure. So it's more like a sphere. It's a more ball-like structure. That's going to be less surface area versus a line, right? So less surface area. 2 balls can't interact as much as 2 lines can. So it's going to have a lower boiling point compared to octane. Okay. Other physical properties, dipole-dipole forces are stronger than London dispersion forces. So more polarity is going to give you a bigger dipole moment, is going to give you greater intermolecular force. That's going to give you a higher boiling point. Basically, greater intermolecular force means greater boiling point, okay? And so if you look at water compared to hydrogen sulfide, water's way more polar. It actually has hydrogen bonding, right? But even look at the delta electronegativity between the 2 atoms. The oxygen-hydrogen change in electronegativity is 1.4 if you do the math. And the sulfur hydrogen delta electronegativity is still polar, but weakly polar. It's only 0.5. And so you're only going to have dispersion and dipole-dipoles in this case. In this case, because you have oxygen, which is very electronegative. Remember, oxygen hydrogen, or nitrogen hydrogen, or fluorine hydrogen, gives rise to hydrogen bonding. So for water, you're going to have all 3, right? So you can predict, the boiling point for hydrogen sulfide is much lower than, it's negative, in fact, negative degree centigrade compared to water. Other things that affects other physical properties that intermolecular forces affect are viscosity. You have more intermolecular forces, i.e. like a more polar molecule or a higher molecular weight. That's going to give you increased viscosity. Viscosity is how hard it is to flow. It's like honey is really viscous, right? It doesn't flow very easily. And that's because it's basically a bunch of sugar molecules linked up together. And so there's a lot of surface area between them. More dipole-dipole and more London dispersion molecules gives rise to increased velocity. Surface tension also will be affected by this, and melting point follows, in general, a similar trend to boiling point. And so that's all we need to talk about, I think, on this